I'm Roger Beecham. I'm a postdoc at the GI Centre at City University, and I sort of finished my PhD a couple of years ago, and that was trying to take data sets from transport systems, behavioural data sets from transport systems, and use them to try and understand travel behaviour. So take sort of new data sets that haven't been used particularly before in that context to try and profile how people move around cities. And it was using lots of visual techniques, and there's also some uncertainty in the data set. But before that, I worked in market research, so I have sort of a short career in data analysis as well. So most recently, I worked at YouGov, which are a big polling agency. And I've been asked to talk a little about uncertainty. And I had to do a bit of reading around, actually, because I sort of engaged with uncertainty in the background, but I didn't really have a detailed knowledge or a sort of more specific knowledge of uncertainty. But I sort of thought intuitively for a long time that visualization and uncertainty are a good match, because data analysis is all about uncertainty. It's all about reasoning about probabilities and trying to hold lots and lots of things in your head and then make decisions. And it seems like visualization may provide a really nice way of taking away some of that reasoning and thinking that you have to do and instantiating it in a graphic. So yeah, it seems like a good match. So I'm going to talk about how visualization can support decision making under uncertainty. So most of the literature on uncertainty that I could find seems to focus on visual variables that are used to represent uncertainty. Things like size, colour value, transparency, fuzziness, sketchiness, and location. So there have been a few papers that have taken these visual variables and done evaluation type studies to see how well these things can represent uncertainty, and they generally come up with recommendations like use location for things that represent accuracy, really general visual variables that have been shown to be good for representing uncertainty, fuzziness, transparency. Sketchiness is an interesting one because it's not been tested too much, but a colleague I work with has provided in processing a library that allows you to use sketchy rendering, and he suggests that it may be used to encode uncertainty information. So here we've got a couple of pie charts showing reported and estimated cases of environmental crime, and the data, which are the estimated data, are rendered this sort of sketchy finish to suggest that these data are, there's some uncertainty associated with them. So that's an interesting technique, but I think perhaps you need to be careful when using the sketchy rendering in particular to encode uncertainty, because perhaps it suggests something else. I mean, I'd say that this sort of stands out a lot more than the reported one on the left. It's very informal as well, so perhaps it's suitable for particular contexts. And when thinking about uncertainty, I think this is the only real visualization guideline that is difficult to find fault with. So things that are not precise should not be encoded with symbols that look precise. I think that's a real key thing to think about when trying to design for uncertainty and visualization. And we're going to look at a few examples of how where visualizations go wrong. So where there are data that are precise, where there are data that are not very precise at all. There's uncertainty associated with them, but they're encoding the symbols that imply some type of precision. So the best example that I've found is this cone of uncertainty. Has anyone seen visualizations like this before? So they're used to represent hurricane tracks in the States. And B is where, so this here is where the hurricane currently is. And then this is a summary of a few models suggesting where it's going to be in the next few hours or days or so. So this black line through the middle represents that trajectory. And this big white splurge around it is where it could be. So this is given these combinations of models where it could be, but the most likely prediction is that it's the black line in the middle. But the key thing to note here is that the further away you go from the back line, the less likely you are to be encountering this hurricane. The problem with this is that this big white splurge is really, really heavy and dominant, and it doesn't reflect that probability. So if you live around about, that can't be reached, but right to the edge of the white line, it implies that you're just as likely to be destroyed by the hurricane as right in the middle of the white cone. Whereas if you're just on the very edge, you're the tip of Florida, you're absolutely fine, you don't need to worry at all. So there's been lots of reporting on problems associated with these cones of uncertainty, because people have to make decisions about whether or not to evacuate their homes based on these types of graphics. And so one solution might be this. So here we're reflecting, this is paper by Van Goughen et al. Here we're reflecting the uncertainty associated model. So the darker the colour, the more the greater the probability that hurricane will be at that location. And the other thing to note is that the boundaries that we've got in this background map are a lot less readable or precise. So maps are really good because they give really, really detailed precision looking at the outline of the states. We've got lots and lots of detail about the coastline and the administrative borders. Here we don't have that. You can't really see it, but you can just, there's sort of light blue here denoting sea and land, but we just have these single lines representing states. So this sort of tries to help avoid a binary sort of thinking about whether or not you're going to be safe or not, and think probabilistically about it. None of these sort of suggestions have been tested, and I imagine for people who live in those areas, a binary decision would actually be quite useful, because then you don't have to think about these things too much. But this is an alternative approach to kind of overcoming the many problems with these cones of uncertainty that don't represent probabilistic nature of the data. So in a similar sort of vein, there's this paper that came out a couple of years ago as well that was looking at error bars. So the de facto way of presenting means and confidence intervals is this plot on the far left. So we've got a bar chart with really clearly defined confidence intervals, and the de facto way of checking whether or not finding is useful is to see whether it is interesting. Is to see whether or not the bars cross. If they don't cross, then that's great news, because then you've got a statistically significant result and you can be really pleased with yourself. If they do cross, then that's hard looking. You probably have to manipulate the data a bit so that they don't cross anymore. So this author came up with these, well actually they already existed, well, these alternative representations which try to represent this sort of probability distribution around confidence intervals. So it's much more likely that an estimated value in the population is close to where your mean is than it is towards the end of your kind of confidence interval range. So these are called violin plots that can be done in R and various other things. And to the left, density plots, where colour lightness decreases the further away you go from the most likely outcome, which in this case could be the mean or the median. So I'm not sure quite what their findings were, but I think they could order these approaches according to how well people performed at estimating the true value of the plots. Okay. So back on to climatology, which I must say I don't know too much about, even though I have got a geography degree. But climatology is a really interesting, I think, one for looking at uncertainty and for visualizing uncertainty, because climatologists, when they try and make decisions about what's going to happen with the weather, they take lots and lots of forecasts from many different organisations, usually with quite poor visualizations to work with, like these here. And then they have to kind of assemble all of those internally in their head and try and make recommendations about what's happening with the climate more generally, or what's happening in terms of short range forecasts. So I think that's a really tricky thing to do. And also, there are certain forecasts which are perhaps more credible than others. So there are certain forecasters, perhaps, that produce better forecasts than others do. And there is certainty associated with all of these sort of visual outputs. So one way of supporting climatologists might be to take these ensembles together and try and represent as much data as possible about those forecasts and what they might be telling us. So here we're looking at climate data, I think a long time ago, 1981 to 1982, in South America. And there's lots of data suggesting whether or not for 1981 or 1982, forecasting whether or not for 1981 or 1982 the weather is wetter or drier than usual. And I can't remember how many forecasts this is built on, but I think it's a very large number. So some were saying that in certain places it was wetter than usual, some were saying that in certain places it was typical, and some were saying that it will be drier than usual. So there are three possible outcomes that we could have at these different locations. And here we're colouring, we're splitting, sorry, there's a term for this, I've written it down, which is common in, they're called terciles. So you have a climate model, and there are three possibilities in this case. One, in this tercile, one is that it can be wetter than usual, one that it could be typical, and one that it can be drier than usual. And so we want to represent these three possible outcomes, including as much detail as possible about them. So here we're using colour lightness to represent how likely it would be that it's going to be wetter than usual, how likely it's going to be drier than usual, and how likely it's going to be typical. So if we compare the right with the left one, they should be the sort of inverse of each other, hopefully, and they typically are. So up around here, Brazil area, it's less likely to be wetter than usual and much more likely to be drier than usual. Another way of looking at this is to take the most likely outcome. So here we saw three possible outcomes in that tercile. Here we're looking at the most likely. So we're throwing away some data, saying, is it going to be drier? Is it going to be as it is normally usual, or is it going to be wetter? And then we're sizing according to something, I don't know quite what, but on the thing on the right, we're colouring according to uncertainty associated with those predictions. So for the top right up there, the most likely outcome is it's going to be wetter than usual, but there's some uncertainty about that likely outcome. We're a lot less certain about the outcome to the right there as we are closer towards the left. But a consequence of taking the most probable outcome is that we lose quite a lot of data, because it could be wetter than usual, where we're suggesting that it's going to be drier than usual. and the reverse could be true as well. So one way of encoding more of that information, or all of that information, not discarding any information, is to use these sort of glyph type representations. So here, the straight line, so you might be able to see here better, this straight line going down is whether or not it's going to be drier than usual and the probability associated with that. Things that are to the left, the line going down is whether or not it's going to be no different than usual. The line to the left is whether or not it's going to be drier than usual, and the line to the right is whether or not it's going to be wetter than usual. So orientation, when you have lots and lots of things on page like we do here, is quite nice because you can see spatial autocorrelation in the values. So here we have lots of things that are pointing that way, some pointing that way, and here we have lots of things pointing this way. So the other thing to note as well is that we're not losing any information here because we've got the three possible outcomes represented with the three possible directions as well. The other thing to note is that here they're all of constant darkness, whereas here we start to introduce lightness, and so that lightness again represents uncertainty. So where things are lighter here, for example, where you often see structures where there's a downwards arrow and a really light arrow to the rightness, the most likely outcome is that it's going to be usual, but it could be slightly wetter than usual. So I'm going to hastily move away from climatology and talk about something which I'm much more comfortable with, which is geodemographics. So do people know anything about geodemographics? So they're used a lot in market research and government research, and the aim is to try and profile really small areas according to the type of people who live there, and then use that as sort of contextual information in the data analysis. So the most common and well-known geodemographic classifier is called the output area classification, and that uses census data, lots and lots of variables, about 150 variables, and it runs lots of clustering algorithms over and tries to identify groups of really small areas that are similar to each other and different from other groups. So there are 7 key, I'm going to come up with the labels here, 7 key output area classification names that people typically use, groups that people typically use that are labelled here. So blue collar living, city living, countryside, prospering suburbs, constrained by certain census typical traits. So once the researchers who developed this classification identified groups that seemed to be discriminating, they gave them labels that sort of resonated with the types of people who live in those areas. But as they're typically used, these output area classifications, we kind of use these big 7 supergroups and take the names for them, so things like this, and use them in the data analysis as a sort of variable data frame that we can then apply. We don't really think too much about probability associated with these things, and there are probabilities associated with them, because this is a parallel coordinate plot of the variables on which the output area classification is based, and we're sort of grouping them by sort of themes. So here are employment ones, here are some socioeconomic ones, here are some housing ones, here are some demographic ones. The line going through the middle, so the dark lines, is the sort of middle outcome. So in the top we're including all output areas that are used in this classification. So I should have said actually that output areas are really small areas of about 150 households in size. So it has some sort of local precision in these classifications. And the sort of varying lightness around it is deciles, I think. So we can see that in the top plot where we look at all output areas, not groups by the classification, there's quite a lot of difference in terms of this housing variable, but less so in terms of these associated variables. Below, we've got the 7 key oak supergroups, so the ones like blue collar, living, multicultural, and things. And the lines that are really dark going through each represent the centres of those groups, and the varying lightness represents sort of distance from the centres, but individual output areas that are part of those groups. So we can see here that the demographic variables, there's lots and lots of uncertainty within a group associated with those variables. So I think purple is, multicultural. So on the multicultural variables, which are used to kind of inform this classifier, there's lots of within-group variation. So for some output areas that are called multicultural, they may not be that multicultural, whereas some may be very multicultural based on this graphic. There's a lot more agreements on these things which are to do with occupation types. So agricultural, the green there is countryside. So it makes sense that everything else is very different from countryside based on that variable. But what surprised me looking at this is that there seems to be quite a lot of covariation between these groups, which are usually regarded to be kind of really distinct. So I've used oak classifications for a long time, and you do sort of take them for red. You assume that they're really nice descriptors for the areas that you're looking at. So another way of looking at this is to plot them on the map. So on the far left is a familiar map of the UK, and we're colouring according to the output area group that is most likely. So a bit like the graph earlier where we were selecting either the maximum probability between wetter, drier or usual. Here we're selecting the most likely group that each output area could be a member of. And so this is typically how output areas are used. We only ever really look at the most likely group. But here on the right we've got plots showing they're sort of maps of the UK, but they're looking at postcode areas and arranged according to their spatial position. So Scottish ones are in the top right. This is London-related ones, and they're sized according to approximate population size as well. So what strikes me is that here we're using colour lightness according to the probability of each of those output areas being a member of each of these supergroups. So what strikes me is that there's not that much variation in these colours, which suggests that maybe the grouping, these output area groupings aren't as well defined as we might have thought. But there are certain ones that clearly are. The other thing that struck me is that there's not that much covariation over space, spatial autocorrelation in these, apart from ones that we'd expect. So multicultural, compared to everything else, these are generally well defined because we've got these cluster of, and there's spatial autocorrelation in them, because we've got these cluster of areas that are very multicultural in and around southeast, so around London. And similarly with prospering suburbs, that's not a very good descriptor for anything that is around London. So we can see that London is very different to everywhere else, but once you get away from that, it seems like these classifiers which try to label and make different lots of areas around the UK, they're not that distinguishable. Actually, because of this, yeah. Yes. So the yellow one is called typical traits, and so usually when you're doing a cluster analysis, it's often the case that you have one cluster group which is not that distinguishable, but is like every other one. So if we forced each output area to be a member of a group, then they'd be a lot like this typical traits one, which is basically the average. It is basically the average outcome across all of these variables that this clustering is based on. So this is saying that there's most areas, irrespective of where they are in the UK, are like this typical traits classification. And the typical traits classification can be roughly understood as the average for the whole of the UK. So average unemployment, average structure in terms of educational achievement. The typical traits one. So that's the interesting thing about choosing the most likely probability. There'll be lots of output areas which are like multicultural, but also like typical traits. And it's the label that is, I didn't explain this very well, but the label that people typically use in data analysis is the most probable. So the closest centre that you're near. So it could be the case, for instance, it could be the case that you're given the output area class of the name prospering suburbs because you're the closest to the centre, so you look the most like prospering suburbs. But the difference between prospering suburbs and typical traits could be really small, so you could be very much like typical traits as well. So we have these 7 groups which try and describe as best they can the types of people living in small areas, but because they're sort of a catch-all, because they're a summary, it's not the case that there's this sort of binary outcome. There's uncertainty associated with those labels that we try to give. Does that make sense? So if there were variation in typical traits.
Well, no, I mean, for instance, looking at the one Luke city living, for example.
Yeah.
So I can see that more people are associated with city living in the southeast. So no surprise.
Yeah.
What am I meant to infer by looking at the two-dimensionality of typical traits?
So from that you infer that there's not geographic autocorrelation in distance from that grouping. So this suggests that most areas of the UK are quite like typical traits.
Isn't that by definition?
It is, but so most areas are a lot like typical traits. But some areas are more like typical traits than other areas. And this sort of contextual information on the background behind oath isn't often used or made available to people who use the definitions.
So this in itself, typical traits especially, helps with understanding the amount of uncertainty?
Typical traits doesn't help with what I'm suggesting is that visualization helps you understand the uncertainty associated with the definitions, or how well defined groups, or how close are groups to these centres. So for multicultural, we have lots of dark and lots of light, which suggests that there are a set of output areas that are really, really close to the multicultural traits. It describes well some of the people living in many of the output areas. And when we look on the map, we see that there's spatial autocorrelation in that. When we look at typical traits, we don't see that spatial autocorrelation. So most places are quite like typical traits. And they're sort of almost equal. It's a simplification, but they're equally like it. So this isn't. This is sort of quite a discriminating grouping, because there are some output areas that are not at all like it, but there are some areas that are a lot like it. This typical traits one describes well, a lot of output areas are not that different from typical traits. So it suggests that it's not a grouping which is particularly discriminating. Similarly, prospering suburbs describes well some of the output areas, because we have some dark, and it also discriminates well because we have quite a lot of light there. So if things are a long, long way from the centre of these groups, so prospering suburbs will be things like semi-detached house, two-car family, those types of things. There are lots and lots of communities in the UK that do have those characteristics, but there are lots of communities in the UK that have characteristics very, very different from that. So the typical traits one is, I suppose what this suggests is that the typical traits output area grouping doesn't really tell us that much. There's not that much differentiation in it. And if we have a output area group which is most like the typical traits one, then we don't really know too much about. Well, the people who live there are not very different from the rest of the UK. Okay.
Thank you for your explanation.
So, well, another way of sort of looking at this and trying to communicate these varying outcomes that we could have, that small areas could have, is through this processing sketch. So I'll just quickly show. Okay, so this is Leicestershire in the East Midlands, and the bar chart on the top left is frequencies for all output areas in Leicestershire and the output area groups that they're most like. So we can see that most output areas are most like the prospering suburbs ones because they have that label. Second is multicultural. Third is blue collar, shortly followed by typical traits. So these are the labels that people use when describing Leicestershire. So we have lots and lots of multicultural around here, lots of the countryside type areas here, and typical traits and blue collar workers around where sort of mining areas are. But there are uncertainties associated with membership of each of these groups. So I was trying to communicate earlier that there are probabilities associated with how likely this area is to be really close to countryside. So it could be labelled countryside, but it could be labelled multicultural, for example. Similarly, this one that's multicultural could be labelled, let's think of a more likely one, it could be labelled city living. So it's closest to the prospering, so this one here is closest to the prospering suburbs one, but it could also be labelled something else. And so what we can do is run a Monte Carlo simulation over this data set lots and lots of times and reflect the probability associated with these things. So we go over and over again these output areas, and you'll see in a minute, each time we show the area that it could be if we took into account this probability. So what I'm going to do is run it lots and lots of times, and you'll see that these bars change in shape. So previously, the prospering suburbs one was really, really long and dominated. The multicultural one was sort of second, and the typical traits was third, and blue collar was somewhere different. If we take into account all of the probabilities associated with them and sort of come up with this sort of empirical distribution of what the actual profile of Leicestershire could look like, these bars in the top left look very different to what they were earlier. So previously we thought that Leicestershire was really, really, really prospering suburbsy and not very constrained by circumstances. For instance, that blue bar was a lot less. But now we see that there's actually not that much differentiation in Leicestershire between these sort of groups, because the bars are sort of roughly similar length. It's still the case that prospering suburbs is just about the biggest group, but actually typical traits is kicking on ahead here.
When you had your reference line earlier on, can you compare it on that graph, on the plot?
Yeah.
Was that typical traits when you averaging the plot?
What's that, sorry? The parallel plot, coordinate plots. So the grey ones, which weren't differentiated by.
The one.
Yeah.
What's
So the top line, so the grey ones, the line going through the middle is the median output area for each of these variables. So we take employment rates, for example, and we have these output areas of which there are about 150,000. We order them according to their employment rate, and then we take the one that's in the middle. Yeah. So there's really big variation in housing and housing variables, less so in some of these socioeconomic variables.
I was just wondering whether that was representation of every
No. So we can see, if you just check that, so the yellow are typical traits, and so we'd expect, not that much differentiation in typical traits. But I'll just go back into it. But if you try and remember the distribution across these output area groups that we saw after running the Monte Carlo simulation, you can see that it is very different to the original one based on the most likely outcome. The other thing to note is that here if you look at the map, it looks very different from the bars there. So if you look at the map, you'd think that most of Leicestershire is countryside. So that most people living in Leicestershire live in sort of countryside communities, and they have those characteristics. But of course, most people in Leicestershire don't live in the countryside, they live in the city, and so if we size these small output areas according to population size and not real geography, so we distort geography a bit and size these areas by population size, we see a very different distribution. Okay, so I've spoken about how visualization can help with understanding uncertainty, how we can encode information that's not always revealed in summary statistics and communicate that to analysts. But it's also true that visualizations can introduce uncertainty in the way that they're configured. So this paper came out a few years ago, Graphical Inference for InfoVis, and it tried to address that problem. So it started off by saying that visualizations are really good because they help us see structure in data sets that would be very difficult to see otherwise, but also that in introducing this structure, it sometimes introduces features that sort of get in our way. So salient features can sort of get in the way of things. So we can make claims very easily based on visual patterns, but we're not sure quite about how likely those outcomes are to be. And so one way of dealing with that is this technique called graphical inference. So here we use some of the theory around null hypothesis testing and apply it to graphics. So here we have 12 histograms. 11 of them are built around assumption of normality, so they're normal distribution, and one of them is a plot discriminating structure. In this case, it's number 10, so it looks very different from the rest. So if an analyst, for instance, is looking at a pattern and he actually thinks it's discriminating, but they're not sure that it might be just due to chance or the fact that they want to see a pattern, they can construct these lineup tests where they build lots and lots of decoy plots around this null hypothesis and see whether or not the real plot still stands out. So that works in this case with these bar charts, but we think that this might be usefully applied to maps. And the reason for that is that maps encode lots of additional information that sometimes can be really, really useful, but also can distort things. So we saw earlier that when we were sizing those areas according to real geography, and we wanted to look at the socioeconomic characteristics of people living in those areas, there was a difference in that most people don't live in Leicestershire, for instance, in countryside areas, but the plot based on real geography was bringing in a distortion. So maps, is what I'm trying to say, can bring in distortions. And we think that these lineup tests might be a useful way of looking for autocorrelation structure in maps. So a key sort of concept in geography is this one of spatial autocorrelation, and that says that everything is related to everything else, but near things are more related than distant things. So things that are similar are more likely to be closer together than they are further apart. And we can see that in these maps here. So this, for instance, could be unemployment rates in a fictional area. And where you have lots and lots of dark colours together, it means that unemployments are very high, that are next to each other, and then the further away you go from any area, they're less like each other. Here, we don't have that spatial autocorrelation. We have something very different. There are lots and lots of differences between these small areas, and there's not spatial autocorrelation in the maps. So we think that we could usefully apply this to looking at spatial autocorrelation in real maps. So we could construct a lineup test where we have a real plot and lots of decoys built under some hypothesis. And if we can easily identify the real plot from the decoys, then that gives us some confidence that there really is spatial autocorrelation in the data set that we're looking at. The problem with this, though, is that the de facto way of looking at autocorrelation is to compare against complete spatial randomness. So that is to assume that there's no dependency between space and the thing that you're looking at, unemployment in this case, and randomly commute these values around to create decoys that look something like like this. But the problem is that complete spatial randomness in space is really, really unlikely. So there's this law that a geographer called Tobler came up with, called Tobler's first law, which is that everything is related to everything else, but near distant things are more related to distant things. So that is that whatever data set you look at, there's always going to be spatial autocorrelation anyway. And if we look at this test here, all of these decoys that we're constructing under that hypothesis just don't look very real. It's very rare that we see plots of unemployment, for example, that look like this. And so we suggest using sort of decoy plots which have some form of background noise in them, background spatial autocorrelation. So here we have a plot which has a really, really high spatial autocorrelation value and lots that have less high values. And so what we're trying to do at the moment is to research a little bit to find out what the thresholds are between people's ability to discriminate real strong autocorrelation structure from decoys where we vary the amount of autocorrelation in the decoys. So I've raced through my talk, but let's have a few questions or discussion.
So thanks for the talk. I've got a question about uncertainty in particular, right? It seems as though you, in order to visualize uncertainty, you have to be certain about the computed uncertainty so that you can visualize it. So is there this recursive argument about your uncertainty of your quantified uncertainty?
Yes, there probably is.
And so how do you do that, right? Like the fuzziness, for example, right? I need some sort of value that I can define how fuzzy I want my line to be. So that means I am certain about my uncertainty.
Yes. So yeah, that exists. I don't think there can be a solution to it. But the thing that we're looking at with the ensemble plots, I suppose, is sort of a solution to it because you're representing lots and lots of possible outcomes, and so that might be a way of providing support there.
I'm going to turn that back. So, as a computer scientist or as a data scientist, you want a quantifiable number of that fuzziness. But when we put this back to the user, if it truly is a blur, they're not going to be able to measure or understand the amount of fuzziness, right? I mean, this is 50% fuzzy compared to that's 20%. The user's not going to actually understand it. So, in that case, for the case of abstraction, just the amount of fuzziness alone at least tells me that it's uncertain. It really isn't important to me how uncertain in those cases. As a user, I mean, maybe you want a quantifiable number, but I don't think you can actually do that if you don't. It's uncertain. You don't really know how it's uncertain. Otherwise, why don't you just do that? 50% uncertain. What would you do?
So one of the things that we started off with was looking at different visual variables that can be used to represent. So you mentioned fuzziness, there's sketchiness, there was other one, and so the empirical research that's gone on was to see whether or not this is sort of a true visual variable. If people can perceive differences in the amount of fuzziness, like you can do differences in length, and yeah, it is sort of more of that relationship between amount of quantity of fuzziness, for example, and a perception of that quantity is there's some interference there. So it is more of a sort of binary type of thing. But yeah, the aim of trying to apply those visual variables is to sort of imply the uncertainty associated with lots and lots of data points without you having to sort of think about it. And I suppose that's the key thing to try and achieve in a visualization.
So we've talked about quantitative uncertainty here. Have you seen or thought about how we approach the qualitative uncertainties that are in the user's head? Maybe, I don't feel 100% confident about this source. I'm I trust this more than I trust that in most cases. But it's a very qualitative representing that as part of them.
So I suppose that would be a really important thing, thinking about the weather examples, because certain forecasters will probably have really good specialist knowledge about the credibility of a certain forecast, and so somehow when we combine all of these forecasts and don't take that into account, then it could come up with a picture that the forecaster doesn't trust. So I'm not sure what a solution would be, but somehow having a forecaster being able to have some effect on the visual outcomes, so determining the weights, the credibility of an outcome.
It seems to me that that's a really important question. And it's almost as if, I mean, that was a great talk, thank you. But it's almost as if there's a whole nother area to be considered, which is to do with non-statistical uncertainty,
Yes.
which is that's not to minimise anything that you said.
Okay.
But that's an interesting thing. Yes, sorry, I've been a bit of a laggard on the microphone.
When you did the work on visualizing the classification stuff, would you say that, having looked at that, you now think that perhaps they need a redesign or a rework because there's such massive differences in the quality of a single classification? For instance, if it's a multicultural classification, you know that that's more likely to be a useful bit of data, or if it's another, that might not be the case. And most of the people that use these on a day-to-day basis have no idea that that's something they should be considering.
So one thing that I didn't mention but sort of was implied in the plots is that that London has a huge effect basically on the cluster groupings, and because of that, the rest of the country looks quite similar to each other. Because London is so different from everywhere else, and within clustering, your cluster group that you end up being a membership of is really relative to everything else, then some people have argued that you should just have a London oak and then have a rest of the country oak. So some people have developed a London oak. One argument, if we were thinking about sort of using visual variables, would be to, whenever you show an oak map, maybe use the most probable area group that you're going to be in, so maybe multicultural, for example, but colour lightness according to how close you are to the centre of that. So then places that we have most confidence in are actually multicultural, have more visual saliency. The problem with that is that people want quite sort of binary distinction. So if you're doing an analysis, and you usually have this oak variable in a column, and you might be looking at some survey data, and you say, oh, well, what proportion of people from these communities think this about green space and those sort of things. It's just introducing this sort of probability range is really, really difficult. It makes data analysis really difficult. So in terms of visualization, it's quite nice that we can reflect this uncertainty. But if you want to come up with sort of quantitative findings that, if you're working in a company, your manager will be happy with, showing them all the uncertainty associated with your findings in the way that I've described might not be that productive, because people will want sort of this binary logic. And so I didn't explain it very well, but the idea of having these lineup tests, which is just an idea at the moment, I haven't seen them being used, might be one way of reflecting the uncertainty, but also coming up with a claim from some visual argument. So you could, for instance, have a lineup test which shows unemployment rates using colour, and something about uncertainty associated with those rates using something else, and then have lots and lots of decoys built on a null hypothesis of those data, and do sort of mimic a formal statistical test, but in the visuals have some uncertainty representation associated with them. So the challenge, which I've not expressed very well there, is we can visually represent these uncertainties, but what happens next when you have to make decisions based on them? And you're working with people who don't have time to sort of take into account and evaluate all of the uncertainties that you're showing them in the same way as a data analyst might. So that was a bit of a monologue, sorry.
Just one comment.
Where's the mic now? Oh, okay.
My name is Stefan. I work for Beecham. We're a geospatial company. And we have never used geodemographic data, but we've used other data that they have similar patterns. And what seems to me is that it's a sort of fuzzy classification when actually each area can belong at the same time on different categories.
That's right.
And then you will have a certain probability for each category based on that characteristics, features, or whatever you're using to describe that specific area. And how we present that on maps is that we use the main category as the color coding, the chlorophyll, and then we use the other categories in a kind of spider diagram, just giving a ranking for each polygon. So the user can just click on each area, and then on the spider diagram, we'll see what's the association for that specific polygon on each classification. If that makes sense.
It does, yeah.
So that in a way, you will have your map, but then if you want to have a more of an insight, you will just click, and then you will have the spider diagram offering you the entire fuzzy classification for that specific polygon. And then we found was a way to kind of solve this issue.
Yeah, so this is sort of happening here. So we have these variables which often are used to inform a geodemographic classifier, so lots of stuff to do with housing and employment status, and these sort of radial charts which represent where you are based on that.
So if you can add dimensions,
Yeah,
that specific area.
and you can see that these are sort of countryside communities. They look a lot different from these ones in cities. I think there's some difference. Yeah, another way.
Something like that. Also, another thing that I think is, I would say, it's quite difficult actually to render on a visualization on a map. Is the difference between uncertainty and model uncertainty or probability, because obviously they're very different things. Because in a way, the model uncertainty, the probability you can quantify, but the uncertainty associated with the data, you cannot quantify that. If that makes sense.
So uncertainty in the data
Maybe
collection.
in the talk was a bit, the two things that were a bit confused. That was my impression. And I think that distinguish between model uncertainty probability and uncertainty with the data like accuracy, precision, and all that, they're very different things.
They are. So I think I should have said at the start that I was only talking about model uncertainty.
Okay.
Yeah.
So I think that then matters up a bit.
Yeah, that's right.
Things.
Yeah.
Okay. Well, Roger, thank you very much. That was. I'm not sure if I feel more uncertain or less about the whole thing.
I'm not sure I do.
Roger, we have a tradition that each of our speakers receives a personally engraved whiskey glass.
Oh, fantastic.
And this is yours, and I'd like to say thank you very much.
Thanks.